Thank you so much. Hi, everyone. Very excited for the next panel because we get to talk about a lot of the work that we've done over the past few months with Decentralized Energy Canada that Anouk alluded to earlier. But before that, we are going to set the stage a little bit. So we do have Adam Benny-Watts that's going to give a little bit of a brief presentation before our panel on quantum advantage in action, talking about use cases will begin. Adam?
Yeah, thanks, Ryan, for the introduction. This is just supposed to be a sort of 15-minute warm-up for the panel, which is going to be the really interesting part of this hour, I think. And I wasn't exactly sure what I wanted to talk about, but the plan, I think, is to sort of give the same sort of spiel that I try to give at dinner parties when I'm explaining quantum and why it's important and why it's interesting. And normally, when I try this at a dinner party, I get cut off about 5 minutes in, and I've got 15, so we'll see what happens. But I'm going to start very broad. I'm going to start very general, and then narrow it down, narrow it down, narrow it down.
I gotta cut you off, sorry.
Oh.
I just want to remind everybody who need the headphones for translation, they're available at the booth, so don't hesitate. Thank you. Sorry, sir.
For sure. No worries.
One more interruption. No, it's okay.
So I'm going to start very broad, narrow it down, and then when we get to the actual sort of technical stuff, the panel will start and we'll have the panel discussion. Okay, there's something else I wanted to say, but I've forgotten what it is, so I'll just go for that. Okay, so let me start by talking not even about quantum. Let me talk about two breakthroughs that we take for granted now that were a big deal once upon a time. And the first one is sort of our understanding of classical mechanics, our understanding of how to describe the world around us with physics, which we really built up finished building up at the start of the 1900s. But this is how we describe mechanics, how we describe electricity, and how we describe things like thermodynamics, heat, energy. And the other breakthrough that we take for granted are computers, which are ubiquitous, of course, but I come from a computer science background, so I'm going to think of a computer as an information processing device, something that takes an input and gives you an output. And so we've discovered computers, we've built them into our world, and we had these two breakthroughs. They were separate, but they also married remarkably well, right? The computers that we've built, these information processing devices, are also exceptional at modeling the world around us, at describing a classical system, right? What I really mean by this is if you want to take a building or an energy generation system or a transmission system or some electrical grid, and you want to model it, you want to time evolve it, you want to see how the system evolves in time, the computational cost to do this scales roughly with the system size, right? If I can model a small system and I want to model a system that's twice the size, I need a computer that's about twice as big or twice as fast. This is iffy. It's not hard and fast, but what I mean to say is that the computers that we have today do a great job at describing most of the world around us. And this is what's allowed a lot of the technology that we have today. So we had these two breakthroughs historically, and they married remarkably well. But the start of quantum mechanics, start of quantum computing, is the observation that this marriage didn't always work. There's places where it breaks down. So in, I think, 1981, Richard Feynman, famous physicist, pointed this out. He said that when you look at a different type of physics, a different type of the world, quantum mechanics, things that are very small, our ability to simulate systems stops to work. So the computational cost of time evolving a system, of understanding how a system behaves, the dynamics of a quantum system is a very difficult computational task. And Feynman was a physicist, and physicists are very frustrating because they sort of pattern match and make things up, and they get it right in the end, but it's annoying that they do. So what Feynman said, I think, I don't know what he was thinking, but I'm going to assume with the sort of physics level pattern matching, is he said, well, the computers that we're building right now, this was in the 1980s, are built with classical mechanics, and they simulate classical systems well. But they don't simulate quantum systems very well. So maybe if we built a system, if we wanted a computer that simulated a quantum system, we need to build it with quantum mechanics. Its inner workings, its sort of processing power needs to come from quantum mechanics. So this was a vague physics speech in the 1980s, and annoyingly, he was right? So he said this then. I mean, he was brilliant. And this was the start of quantum computing. If you go forward about 10 years, the 1990s is when we really started to formalize these ideas and figure out exactly how right he was. So we sort of, 1992, someone called David Deutsch gave some of the instructions, the proper description of how a quantum computer should behave. Seth Lloyd, 1996, really formalized this idea of Feynman's. He said, okay, yes, in fact, if you built a quantum computer, it could simulate a quantum system. Here's how, here's the rules, here's the algorithm. Okay, and with these two results, you have sort of a niche but neat, sort of technical observation, right? That there's this type of physics. If you want to simulate it, if you want to time evolve it, you need a quantum computer. Here's what one would look like. But it wasn't really clear what or why or how or if these things would ever be useful. But there's two more breakthroughs in the 90s, both due to Peter Shor, who deserves a lot of credit, that moved quantum computers from sort of the abstract to at least the abstract and maybe useless to the abstract and maybe useful. So Peter did two things. First, he talked about quantum, well, I'm getting them out of time, but I'll say it this way. First, he talked about quantum error correction. So there was a notion beforehand that a quantum computer, it's an abstract idea, but it's never going to be something that we can control, that we can tame. There's always going to be noise. For people who are maybe a little more technical, there was a worry that these things were just sort of analog computers that couldn't be digitized. You don't get a clean input, you don't get a clean output. You're never really going to build a useful one. And what quantum error correction showed us was that actually that's false. There is a way to control errors to get clean inputs and outputs out of these machines. The other thing that Peter Shor did was he showed a use of these machines that had absolutely nothing to do with simulating quantum systems. So if you've heard about factoring, it gets mentioned in the news. He showed there was a math problem of breaking a number up into its prime factors that you could solve on a quantum computer that you couldn't solve classically. Okay, and this is interesting for a few reasons. This is interesting because factoring is important for cryptography. This is why people talk about quantum computers breaking crypto systems. But it's also interesting because it showed that these machines that were developed for a very specific, at least conceptually developed for a very specific idea, right, simulating quantum systems, might be useful for completely different problems. There might be problems out there where our computers right now struggle, hard problems, and if you built a quantum computer, you could solve them. So this sort of opened the door to the idea that these computers might actually be useful for a wide variety of problems in practice. And so this was maybe the dawn of some of the dawn of some of the excitement around quantum computing. This is when at least theoretically these machines were conceptualized. We could build them. If we built them, they would be very interesting. So that's the 90s. I'm going to skip ahead to 2015. Lots of interesting stuff happened in the meantime. It's just that 2015 is when I started my PhD, so I sort of know better what's going on. But 2015, I started my PhD. The theory of quantum computing had been developed fairly significantly. But I'd say, I was a theorist, so amongst the theory folks, if you asked people, opinion was probably about 50-50 on whether or not you'd ever see a quantum computer in your lifetime. And not even your academic lifetime, but just your lifetime. So these were machines, we were theorizing about them, we were playing around with ideas, but a good chunk of the community thought these machines would never be built. It was just a math problem, and an interesting math problem. But over the course of the 5 years of my PhD, opinion started to shift. There's a lot of excitement around what was happening on the hardware side of things, what companies were doing, how these machines were progressing. At the time, it was Google that was really leading the way with superconducting qubits, a certain type of technology. But the words that started to get mentioned was this notion of quantum supremacy. So this is now an old headline, but in 2019, it was the breakthrough that we were all pushing towards. Quantum supremacy So this was a landmark result published by Google in 2019. They had a quantum computer that achieved this task of quantum supremacy. It was using this computer, a quantum device, as an input-output machine, not to do anything useful. In fact, a task that's almost useless by design. But the argument was, you need a quantum computer to map this input to this output. You've got sort of an input-output box, and there's no way to simulate it classically. Okay, only a quantum computer can do this task of mapping this sort of fairly noisy input to this fairly noisy output. But they published the paper, there's a strong theoretical argument behind it, there was a back and forth, but certainly now it's established that I think largely agreed upon that we have computers that are capable of these quantum supremacy type demonstrations. So we have machines that, at least on a very theoretical level, can do something that no classical machine can in a reasonable amount of time. I mean, there's caveats here, but we're at least doing something with quantum computers that we couldn't do otherwise. Okay. And now if I think back to 2019 when this first happened, I mean, this was very exciting. It was a demonstration of the fact that these machines could be built. But the task was useless, right? The task was not meant to be useful. And these machines still had limitations. They were noisy, there were errors. And there were sort of two schools of thought at the time. The most initial sort of excitement back then was to say, well, we've got these input-output boxes that can't be simulated classically. So all we've got to do is tweak them, shake them up a bit, make them do something sort of interesting, and then we're going to find uses, right? I mean, once you have something that no classical machine can do, it's very tempting to say, okay, I'm just around the corner from some breakthrough commercial application, right? Maybe it's not going to take very much work or effort to make these machines commercially viable or useful. And I'm mixing things together, but let me say that this is sort of the philosophy behind what was called NISQ, Noisy Intermediate Scale Quantum Computing, where people said, we have these machines, they're imperfect, but they're doing something interesting, and so maybe if we just shake them around a little, tweak the parameters, we're going to get something commercially viable. That was a philosophy that sort of followed supremacy, so early 2020s. This was a lot of the feeling, motivation, sentiment in, I guess, the intersection of quantum computing and business. And I don't want to be too pessimistic, but I will say this wasn't as successful as we hoped, right? I mean, these NISQ devices, this sort of take the noisy machine and tweak it a little bit philosophy, has produced results that are competitive with your standard breakthrough classical approaches, but they're not order of magnitudes better. They're comparable maybe, but we're not seeing a breakthrough performance where we're seeing a perfect use case of these sort of NISQ quantum computers. And so this has left the field in an interesting place. And there's now I think there's two ideas, both very important, and I'm going to try and stay neutral between them, but I just want to set the scene. One says we have these NISQ devices, and maybe we push these ideas a little farther, right? The hardware is getting better, it's improving. Maybe we can tweak the performance a little bit and start to see more of a quantum advantage, more breakthroughs, more utility out of these machines. So there's sort of this scale-up NISQ approach. There's another philosophy that says, if you think back to the 90s, what really was exciting to us about quantum computing was this notion of error correction, that we can get rid of noise on these machines, that we can control them very carefully. And the machines that we have right now aren't quite good enough for error correction. We're starting to see it, but we're not using it particularly. But that's coming. Again, if you look at the hardware roadmaps, if you look at the most optimistic hardware roadmaps, where maybe 3 or 4, 5 years out from sort of error-corrected quantum computers. So when we get these, you unlock a whole new wave of applications. Now you've got much more careful control over this machine. Maybe you see some interesting use cases that you didn't see before. So maybe that's where sort of the commercial viability lives in algorithms on these error-corrected quantum machines. But the thing I'm going to point out about both of these approaches, sort of the scale-up NISQ and the error-corrected philosophy, is that the time has come where we need to stop just talking amongst ourselves as quantum computing researchers and start taking these ideas, these algorithms, either the error-corrected ones or the sort of NISCI ones, to industry and talking to domain experts and sort of combining ideas and seeing where the actual use cases are and how we can map these sorts of algorithms onto them. So, sort of regardless of whether you believe in, well, or both, but regardless of whether you put your bets on error correction and fault tolerance or sort of near-term quantum algorithms, the test is going to be how well these algorithms can be applied to industrial use cases and to real-world problems. And the benchmarks are going to be not sort of theoretical, but state-of-the-art methods being used right now in industry to solve problems. And this is what we need to start comparing against and competing with. And so that's sort of all just to set the background for what we're going to talk about for the next 45 minutes, which is how these algorithms and decentralized energy might start to interact with each other. So, thanks.
Yes, please stay up here. Thanks so much. I feel like I've had the privilege of listening to your talks over and over, especially over the last couple months. And for someone like myself, I just keep on learning so much more. And that's one of the things, especially Quantum City, we really want to be, those trusted, honest advisors for industry, for those folks that are looking to adopt quantum technology, and how can we bridge that gap. So I'd like to welcome the rest of our panelists up here on stage. So please come on up. Andrew Muir from Schneider. We have Brent Harris from Iguana, and then Alexandre Choquette from IBM. So instead of me having to read a bio for each of you, I know, there might be some mic sharing here, but Adam, how about let's start with you. Just a little bit of an intro. I know you met everyone, and then we'll just work our way down.
Yeah, you make me think I should have done this before I started talking. Yeah. Hi, everyone. I'm Adam. I'm a professor of mathematics at the University of Calgary. Before this, I was a scientist in residence at Quantum City, so I got to work very closely with the Quantum City folks. And before that, I did a postdoc and a PhD studying quantum algorithms. And I'm Canadian. I grew up in interior BC, and now I live in Calgary. So, split loyalties.
Thanks. Andrew Muir with Schneider Electric. I've been with them for over 20 years now. I am the director of our strategy for what we call our digital energy business, which is really focused around building automation, power management, and microgrid solutions. So I'm looking forward to this discussion. It's going to be good fun.
Good morning, Brent Harris. I'm the Chief Operating Officer and founder at Iguana Technologies. We manufacture and deploy residential energy storage systems for grid services, really building VPPs to support grid modernization.
Hey everybody, I'm Alex from IBM. I do research ecosystem development for strategic geographies all over the world. I have a technical background in quantum computing from University of Sherbrooke, so I grew up in the Sherbrooke ecosystem, has been mentioned a few times today, and I'm now based in Montreal and on a plane.
So just to kick us off, we'll keep this part very, very brief. I just want to hear from each of you. What excites you the most, both from an industry and a quantum industry perspective, about the potential of quantum technologies? Just based off I'm looking more at the industry side, just based off what you currently know, what are you excited about? Andrew?
Sure. So as we've talked about today with traditional computing, traditional sensing, things like that, we have a pretty good grasp of what that does and how that's applied in our industry. From the quantum side of things, it really starts to become exciting when we start to look at, well, one, I think cybersecurity obviously is mentioned earlier today. That's going to be one of the top topics for most people, especially if we're looking at utilities or industrial processes and things. We want to make sure that data transference is cyber resilient as these technologies come on. But then going beyond that, what kind of applications are possible with leveraging the quantum space, right? So things like sensors. Are we going to be able to start sensing information and electrical distribution networks that we didn't know about before, and being able to be more predictive in how we approach things. If we're looking at modeling and simulation, what kind of things can be unlocked using quantum computing that we never had before. So there's a lot of interesting spaces that we're looking to explore, which I think is going to be really impactful within the industry.
I can just add, I agree with everything you said there, Andrew, but for me, it's still learning what quantum can do, and I think the fundamental learning, we're not going to be doing a lot really new that we haven't done in 100 years. Electricity is still electricity, but it's all getting more complex, and as I learn more about quantum, it's highlighting a way where we're going to be able to make better use of this increasing complexity, distributed energy systems, and stacking value and getting the most value out of the assets that we have.
It's a tough one, right? Because quantum is a fast evolving field applied to another fast evolving field, right? And trying to pinpoint what is the most exciting thing that it's going to come up is pretty much impossible. But let me give you the side with Adam and give you the physicist answer. So on the one side, quantum, we're putting this very new and exciting and seemingly very powerful tool in the hands of very smart people that know what problems we need to solve. And so just the fact that we have a new tool to solve new problems will eventually lead to some very interesting things happening with this technology. So yeah, the fact as a physicist, just the fact that okay, now we have this new tool and we can throw it to the world's problem and find new solutions that we didn't have before. Just the simple fact is exciting to me.
Adam, anything to add there?
Yeah, I think I'm going to agree with Alex here and say the same thing but differently. But it's that for a long time we've had these quantum algorithms that were just sitting around, but our only understanding of them was theoretical. We couldn't run them on machines, and we weren't really seeing them in practice. And now we have the opportunity to throw some of them out there and see how they perform. And it's hugely exciting, because it's always harder to prove that something's going to work than it is just to test it out and see that it does work. And so we start to see that opportunity coming, and I'm very excited about that.
And just to add on that, neural networks have been around since the 70s, right? But it's only when we had hardware that could actually run large-scale neural networks that we saw AI take off, right? So we're kind of this inflection point where we have some algorithms, and now the hardware is becoming interesting enough to start running things on it. Probably not large-scale enough to run the quantum neural network of the future, right? Or what's going to be the ChatGPT moment of quantum. But we're getting there and starting to see all these little pockets of innovation coming up year after year. I think, yeah, that's poised to be exciting.
Great. So just for everyone in the room here, I do promise I will leave some time for questions. So if you've got anything, just keep that in mind till the end there. One thing we do with our discovery sessions, and that's kind of what we'll do a little bit for this panel here, is really set the, what is the problem that industry is facing? So we'll start with that side of things and then see how quantum can address it. But that being said, one of the things that I often hear when I talk to people about exploring how can we, help bridge that adoption gap is, trying to find problems. Industry is often trying to find problems that they think can be quantum relevant. And one of the things that we did with both Brent and Andrew, were two of the first to put their hands up to these discovery sessions, was really just talk about, what are the quote unquote unsolvable problems that your industry or organization may have. And then it's up to us and the quantum physicists to help determine if there are quantum technologies that are applicable. So as you're, if you may be exploring this quantum journey, you don't need to think of problems that you personally think may be suitable for quantum. That's where the quantum folks will be able to help. So I just want to start with that and kind of level set. And then for either Brent or Andrew, either Iguana or Schneider's perspective, what are some of those big industry problems that you're currently facing?
Well, I think the key problem is the one Nils mentioned earlier this morning, is load growth, which has been a characteristic of the electric industry for the last 120 years, except for the last 20 years. With energy efficiency coming on, we've kind of had this pause in the electric distribution or transmission and distribution industry, where even though there's population growth and increased economic activity, the peak load on the electricity grid has kind of been flat. And so every year when utilities look at their planning decisions and go to the regulator and say, well, we need to spend this much money to maintain our equipment and we need to add capacity, they're not really able to justify major investments because, well, you know, everybody's getting energy efficient appliances, everybody's switching to LEDs. You know, the peak load isn't going up, and that's really, you know, it's the traffic jam that Nils was talking about. There's no traffic jam. Why do you need a wider highway? Suddenly, we're hit with electrification of vehicles. We're hit with these data centers, switching from gas to electricity. So at the same time, well, we've hit the end of the road on energy efficiency improvements. Everybody's got LED lights now. Now we're adding these vehicles and all this other load at the same time as it's become very difficult to build new infrastructure. Fortunately, we have new solutions available, digital solutions, distributed energy solutions that can solve the problem, but they bring a level of complexity that distribution planners haven't had to deal with before. And I think that's fundamentally the opportunity for Quantum and any other solution that we can bring to our industry.
Yeah, no, well said there. You know, on top of that, or adding to that, when we start looking on the demand side of things, our facilities are getting more and more complex. There's more and more data that's coming in that we're using to optimize production, ensure comfort within a facility meets the standards, right? The government's implementing different standards on us for how energy efficient facilities can be. So we're dealing with more and more complicated data. We're dealing with, frankly, more and more sensitive equipment. When we start talking about data centers, we're talking about pharmaceuticals, where historically we had a lot of equipment in the field that was, you know, that could go through, you know, power surges and dips and ride through. Now we're dealing with solid state equipment that's either on or off. And so trying to be able to protect that equipment, understand how the energy is being used within your facility to either improve your production capabilities or to reduce your energy consumption, to ensure that we're not adding more load to the grid that we don't have capacity for. It starts to become really complicated to try and understand how to do this. And this is where we're thinking that, you know, quantum technology could, you know, be helpful there. Just like Brent, I'm not an expert in this field, but I'm seeing what's happening out in the industry and seeing if there's a way to match that.
Great. So bringing the experts into this, I'll start with Adam. Based off some of those problems or things that industry is dealing with, what is feasible right now with Quantech when we look at more of the near-term applications? Like, what can companies start either testing or practicing, or how does that look like? What does that look like, sorry?
Sure. Maybe the lowest hanging fruit, which is too broad, is to say, you know, in both descriptions, I sort of heard behind the scenes some amount of optimization, some amount of scheduling, some amount of these sorts of difficult optimization, scheduling, tasks. This is a place where these are natural problems to throw at near-term quantum computers. It's a very nice playing field for us to test out algorithms, test out ideas, see what happens. The caveat is this is exactly the field where you're probably not going to outperform state-of-the-art classical by much, or you're going to be competitive with state-of-the-art classical, but it's a great place to dip your toes in and start seeing what quantum can do, and maybe over the next few years be surprised.
And then, so Alex, maybe you could either add on to that, but then also from IBM's perspective, looking more at the fault-tolerant computer, what do you think quantum computing may be able to help address down the road?
Well, so is everyone familiar with the difference between a NISQ computer and fault-tolerant quantum computer? Who's familiar with the difference? By show of hand. Perfect. Okay, so as Adam explained, like right now we're in quantum computing. We're at the stage where we're starting to see maybe 100 or 150 physical qubits being on a chip. But the problem is that don't get fooled by numbers. These qubits are entirely noisy. Okay, so the lifetime of the information relevance inside a quantum computer is very limited now. So in terms of the number of operations that you can do on a quantum computer, you won't solve many real-life problems today. So what you need to correct for these errors that happen naturally in the quantum computers. Because as Adam said, it's based out on quantum mechanical principles, which are very finicky and the same physics that describe atoms, right? So whenever it interacts with the rest of the environment, you lose data basically. So luckily, there's a tech that's called quantum error correction. And for many, many years, it's been theorized that in principle, it could work. So the way it works is that you take many, many physical qubits, depending on the technology, can range from a few physical qubits or a few thousand physical qubits. And they're all noisy, right? And you make them all act as one perfect logical qubit, whose lifetime is a lot longer. Okay? And then if you pair many of these logical qubits or clusters of noisy physical qubits and you run this error correction protocol, then you get many logical qubits, and the lifetime of the computation that you can do is a lot greater. So that's a paradigm of what we call fault-tolerant quantum computers. So they are tolerant against errors or faults. So that's like the paradigm that everybody's kind of aiming for, right? And all the first algorithms that came out in quantum computing, like Shor's algorithm and Grover's algorithm, who solve optimization problems, they're all like fault-tolerant quantum algorithms, meaning that no quantum computer today can run these algorithms in any way that's meaningful. And so we're all waiting for kind of this point in time. And if you look at many of the hardware vendors, roadmap, IBM included, Pascal included, many of these companies or hardware vendors are predicting that inflection point to happen around 2028, 2030. Okay, so that's kind of the date you have to have in mind when it turns on. So that means we're all going to turn on error correction, and all of a sudden, the capabilities of quantum computers is going to increase by a lot. So we might be able to run these fault-tolerant algorithms. But 2029, say, is kind of almost to tomorrow, right? If you know nothing about quantum, right, you need to kind of start today to try to understand what quantum can do, and to start building algorithms and also your portfolio of IP, right? Because if you wait until then all your competitors might have already developed or built the quantum teams. Now, going back to the questions, because I'm diverging now. Okay, did that help? I hope that helped you understand a little bit. Perfect. Okay, so many things. So once, when we get to fault-tolerant, we can run these large-scale optimization algorithms or Shor or anything, and so that will kind of be, say, easier to take a really hard optimization problem for classical computers today and kind of throw a canonical fault-tolerant algorithm on it and hoping for the best. So that's on one thing. Then also what's I think one thing that is going to be interesting is that there's another quantum technology called quantum sensors, right? And so I don't know what the state of quantum sensor adoption is in the energy sector, but I can imagine that we're going to see more and more sensors in like microgrids or smart grids that produce quantum data inherently. Okay, so the data that comes out of the sensor is quantum by nature. And so if you plug that sensor directly into a quantum computer, without encoding it into classical data, so you kind of keep the quantumness of the data, plug it directly into quantum computers, then you might be able to extract a lot more value out of this data directly. And so, IBM included, but many vendors were building these quantum internets, or these ports that are coming out of quantum computers and that will be able to connect directly to quantum sensors. So say you have a data center somewhere, it's connected to the grid, then you might be able to collect the data directly from the grid onto the quantum computer, treat it there in some sort of quantum machine learning algorithm, and then make a lot more sense of the data coming out of the grid. So both on the algorithm side, but also on collecting sensor data. I'll stop here.
Thanks. So then, Andrew, I'll turn to you. Kind of, I'll touch on a little bit just on what Alex said about like these timelines coming up. So, what do organizations like? You put your hand up to do this discovery session. So, how do you start those? For some folks in the room here, how do you start those internal conversations within your organization that like you want to start exploring quantum? What does that look like? Where do people begin?
That's a big question, I think. So a lot of it starts honestly with curiosity. It starts with conversations that our customers are having right in the field, right? They'll come up, hey, have you heard about quantum technology? Other companies will have quantum researchers that are starting to dive into this space, and they want to work with us and help us understand what they're looking for so that we can help them solve these problems. So within an organization like ours, we develop pockets of experts in the field, right? We will bring in quantum experts to start having these similar types of discussions we were having on what's actually happening in the industry, and having them sort of apply their knowledge to help solve these problems. But really, we really want to be driven from what the customers are seeing, what the industry is talking about, and how do we fit into there. So a lot of times it can start organically, right, with just people being curious and having these discussions. And from there, as momentum builds and more people are asking these questions, it starts to build momentum internally, and you start to get much more focus in these spaces. Yeah. And
then, so I do want to talk about our discovery sessions that we did, but maybe, Adam, do you want to just kind of briefly touch on the work with Schneider and Iguana that we did? Kind of like, what were some of your learnings from a quantum perspective that you got out of it? And then Brent, afterwards, I'll kind of go to you to see kind of what you got from that initial session.
Yeah. Maybe it sounds silly to call this a learning, but every time I do these sessions, I'm always really excited by sort of the depth of industry expertise that I'm exposed to. It's you sort of view a lot of problems at a flyby level, where you think, oh, that's an optimization problem, and that's all you learn about it. But the more sort of domain expertise you bring into it, the more domain relevance you bring into it, the problem gets a lot richer, and I think that's very valuable. So I mean, learning the specifics, learning the motivations, I think was very exciting. And I think the other thing that was exciting was just how rich a set of problems there are out there. That there's a luxury of problems that you could try and apply a quantum computer to, which is sort of scary because it's hard to pick the best one, but it's exciting that there's so many that you could take a swing at.
And then Brent, so what did you learn about, learning more about quantum in those sessions and how it can be applied? What were, from an industry perspective, what were some of your insights?
I think it was a pretty interesting process. I think we just did one session. It was about 3.5 hours, and it was interesting because the quantum researchers were trying to, of course, we were like the experiment, and they didn't want to interfere with the experiment, so they didn't want to give us too much information. So it was kind of like a bit of a dance around sharing information, and we just start talking and see where there's kind of some alignment and say, okay, maybe let's go down that path a little way. I guess I was surprised to learn more about quantum through that process and kind of build a heuristic model of what quantum is from our perspective, which is really it has the potential to solve problems that are growing in complexity. We can manage them today, but you can see where it's going to become difficult to manage, and that's the hope, I guess, with quantum, is that it can start to solve those problems. And the other one is, that really highlighted for me is, the problems we came up with are not new problems necessarily. They're just problems that are becoming more significant and more complex to solve. The one that came up was just generator stacking, right? So in your power system, you'll have big generators and medium generators and small generators. As your load increases, how do you decide when to turn on the big ones or the small ones and all that? I mean, we've been doing that for 120 years, and it pretty much works. But as you move from a handful to a dozen to thousands and millions of generators out there contributing to the grid, it becomes a much more complex problem to solve. So, I mean, I don't know if I've really answered your question, but it was an interesting process to go through, and I'm interested to see what the next discussion is going to be about and how we can drill down.
And then, so Alex, with the sustainability working group, which you can touch on because I'm not sure if anyone here is too familiar with it, but what kind of use cases are there? Because I know you weren't in our discovery sessions that we did, but what kind of use cases are you currently working on that is out there that have already happened? What does that look like?
Yeah, great question. So another role I have at IBM is that I'm leading the sustainability quantum working group that we launched. So at IBM, we very early realized that we can't do it all. Like we can't be building quantum computers and plugging it into a cloud infrastructure and selling you access to quantum computers and then plus developing applications and use cases and working with all sectors to solve everybody's problem, and we can do it all. So we're gonna stop at building quantum computers because that's what we know how to do best. But then we're gonna work with the community that know what problems are relevant to solve, and we're gonna pair them with quantum experts, and hopefully we can come up with relevant applications. And so one way that we had for that is to we launched 5 technical working groups. So they're international communities of technical experts, both on quantum, classical like AI experts, and domain experts that come together to think about quantum computing applications for X field. We have one in like optimization, material, high energy physics, healthcare and life sciences, and then I'm leading the one in sustainability. And also sustainability does not mean much, right? It's a very broad and broad term. So we are focusing on, so I would say it's maybe like 50%. Adam is part of it, so I'm looking at him. So I'd say it's like maybe 50% energy sector. Then we have use cases in like semiconductor supply chain optimization. That's a huge industry. In wildfire prediction, as well as battery designs and even like sustainable concrete. So if you want to build concrete, we want to have low carbon concrete. Anyway, and then in the energy sector, we're working with energy providers like Hydro-Quebec. E.ON is also part of it, so they're managing the grid in Germany, and they're quite big. So they have a team of quantum experts, roughly 5 people maybe at E.ON, and their leader is Canadian, so he's happy to collaborate with us and Hydro-Quebec. And so the themes that are explored there, and so for example, Adam is leading a project on the unit commitment problem, so he can tell you more about that later. We also have AC power flow calculations, and I'm forgetting other ones, but so we're taking all these experts, looking at what quantum can do, and also comparing it with classical state-of-the-art methods, right? Because ultimately, we're not looking for a quantum solution to a problem, we're looking for a solution to a problem. So if it turns out that, no, actually AI is better at tackling this problem or in this regime of parameters, then so be it, like, let's go with an AI solution. And also, you need to be able to match the timeline at which you need a solution with how quantum computing is going to evolve, right? So if it's a solution that you need, in real time in the next 6 months, then quantum is probably not the right tool for your problem. So we're kind of basically bringing a lot of smart people and tackling this exercise together.
And then, so for the quantum physicist here, where does industry start? How do they begin this process? I mean, you've got 2 industry folks on the panel here today. Where do these folks in the room begin?
Yeah, let me. I'm going to talk quantum specifically because this advice is maybe a little different if you're looking at, say, AI or something else. But if I'm allowed to be a tiny bit negative, something else that came out of the discovery sessions is that problems are hard for a lot of reasons, and a lot of problems are just hard because you're dealing with a massive amount of data. It's an easy information processing task, but it's a massive amount of data that you want to process. And this is a place where quantum computers probably aren't going to be useful. They're not a brute force speed up, and they're not necessarily better at dealing with just larger amounts of data. So really filtering out the problems that are due to data size versus the problems where there's actually some complexity of the information processing that you want to do. where the where you're looking for some complicated correlation. There's some difficult there's a difficult task that you want to do with a smaller amount of data is sort of a good entry point for quantum. So sort of filtering your problems through what I would call a computational complexity lens is very helpful, I think, because then you at least know the good candidates for quantum. And then it's just a matter of playing around and seeing what quantum can and can't do, I think.
And then so on the industry side, what do you need more of from the quantum ecosystem? Like what is missing? What are you hoping for? What does that look like?
So, yeah, it's a good question. So, I think both Brent and I, when we were part of these sessions, as we were saying, we were learning just as much as I think the team was learning on, what are the right connections. And as Adam was just pointing out, I mean, something that, for example, we came up with and through the discussion was this concept of digital twins, right? You've got a facility layout with your existing equipment. You want to change things, you want to move things around, you want to understand what impact things are going to have. Doing a digital analysis of that isn't so much a lot of data, it's a complex problem that quantum could be something to solve. So, I mean, I think everyone in the industry's heard of this term, digital twin. In quantum, it's really like the old traveling salesman problem or optimization problem. We were both talking about the same thing, but from two different angles. And I think honestly, just the fact that having a discussion kind of connected that. I mean, that's just one of the many points, but connected that really helped, right? So I think before I was coming into the session, I heard of quantum. And then after we had these discussions, well, there's quantum computing and there's quantum communication and there's quantum sensing and, just even understanding a little bit more about what these things are. And then starting to think about, okay, if you take the word quantum out and you apply that to what we do on a daily basis, are there things that we're doing in a communications way, for example, that we know is going to get more complicated and we don't know how to solve the problem? So I guess it's a long way of me saying the best way to understand is I think to have these kinds of discussions and really trying to simplify a complex problem so that you can think about the problems that you're currently having in a way that would fit into how a quantum scientist or person would need to consume that information. I think that for me was a big piece, right? Like is how to make that kind of communication and understand what they need.
I'm just gonna jump on that for a sec.
Yeah.
Maybe I was just going to agree with you basically and say that I think as you were talking, I was realizing I think what's really valuable are these discussions, and I'd just add that if you have a 1 hour discussion and at the end of the discussion you hope to nail down the perfect use case, it's probably not going to work and you're not going to come up with the right use case. But I think these just sort of open-ended information sharing back and forth, learning each other's languages is really, really valuable and really important. And we need to do a lot of that before you arrive at, I think, the best use cases.
I would just echo the same thing for us. And for me, as part of the session, it's still a very abstract concept, and there's a leap of faith where it's just imagine this works like this, and what kind of problems could you bring? To kind of scale that up and bring it into our business and say, okay, we're going to look at applying quantum here. It's going to have to get a little more concrete before we can engage that level. But I think you're right. There's only one way to get there, through discussion.
Yeah, I would say in short, in 2025 or 2026, everybody should have some level of quantum strategy or quantum roadmap. And it's okay if your quantum strategy is, we've looked at it, it's not for us right now, we're going to look at it back in 2-3 years, right? It can be a one-pager, right? But I think every company should have some sort of quantum roadmap. And look at what you're doing with AI, right? It got so much attention, and you're like, okay, if it it can solve this or that problem in that industry, what can it mean for me? And quantum will be maybe kind of a like slower but higher potential type of technology. Because one thing that we're mentioning is, I'm sure you get the feel that it's a bit different than just how GPUs came up to be, right? Because it's based on an entirely different physics down there, right? Because ultimately CPUs and GPUs, they operate the same, like it's the same logic. It's classical logic that's under them. And quantum is the first, say, computational innovation that has promises of exponential speedups for certain problems. That was never the promise of GPUs, right? So you can see the potential that quantum can have. So I would say, have a look at it. Look at what use cases you have. Educate yourself. What can quantum do today? What we expect it to be able to do in the next 4 years. And yeah, come up with a draft one-pager strategy for that.
And for everyone in the room, if you're not, comfortable with quantum or have an understanding, I think what I heard from, both Andrew and Brent is that's okay. That's normal. Just starting those conversations. Like, it doesn't have to be this super overwhelming thing. It's just begin the conversations, and then we can have more talk sessions and then see how it can really be applied. So quantum tech is very industry agnostic. So are there, use cases in other industries that you think could possibly be applied within the energy space?
Yeah, that's a good question. So right now, our scientists were trying to find out, okay, can we find out fundamental algorithms that would be horizontal across industry? And we've identified 4 areas where we believe there's going to be a high impact for quantum. So the first one, it's going to be a bit technical, but it's called Hamiltonian simulation. Okay. So what does that mean is think of material simulation or chemistry, anything that has to do with atoms and molecules that you want to simulate. As Adam said, they behave quantum mechanically, so therefore quantum is better suited for them. So Hamiltonian simulation. The other one is optimization. So no need to explain to you what optimization is. So we know quantum will have some sort of speed up. The question is at what scale and when. Then the third one is partial differential equations. So I think computational fluid dynamics simulation, for example, Navier-Stokes equations. That's another area where we believe quantum might have an impact. And then the other one, a bit more exploratory, is machine learning. So there's a lot of data. It has a lot of different structure and different volumes. So it's unclear whether quantum will have an impact on all type of machine learning. I don't think so. But for sure, there's a subspace of the whole field of machine learning where quantum will be transformational. So now if you start from these 4, say, horizontal layers of application development, then I'm sure you can think of many verticals that can stream out of that. And some applications would be the same in many different sectors. For example, just today, I've been hearing a lot about peer-to-peer trading, right? So I'm sure that some applications in the financial sector might apply well to the energy sector, but I'm sure you guys already know a lot more than me about that. So yeah, also.
We've got about 8 more minutes left here, so I am going to open up to questions to the floor. Okay, we've already got one. Great, because or else I was going to have them question each other. I think they're going to come bring a mic. Oh, do you want one of these mics? Okay.
Thank you. Hey, it works. Kay Aiken, CEO, Dynamic Grid. So call me a quantum skeptic. The material science totally get exactly. Thermodynamics, great use case. But in energy, we're talking about complex systems and optimization. And generally, the way I understand it, we're looking at quantum solutions that are trying to do global optimizations on the energy sector. Because of the way this, maybe in 20 years, it might be different. We might be able to get a quantum computer on this. That's possible. The problem is when you're trying to do global optimization, as a grid architect myself, is we're now working with large data streams, communication, ubiquitous communication, tier bypass problems, with the optimization. We have a whole host of problems where we are the decentralized energy forum here, and decentralized energy systems can do this much more effectively than trying to layer on. The utilities are traditionally, centralized. And we're here decentralized. So I'd love your opinions on that.
Yeah, I'll start, but I bet you, Alec. I'll start. I think I think I pretty much agree with you, and I think it's a great point. So, yeah, I guess I think this is agreeing with you, which is to say that most optimization problems out there, you're probably not going to use a quantum computer for. One of the reasons is that if you're solving the problem already with your classical device and you're solving it, well enough. Or perfectly, then there's no reason to push it off to a quantum computer. If you're already solving the optimization problem you care about today, don't move it over to quantum. Where there might be a use case for quantum, the easiest things to talk about are situations where you're not getting the exactly solving the problem. You're sort of approximately solving the problem, and you could hope that even a 1% better solution has some large cost advantage to you. If you're getting 98% of optimal, but pushing up to 99% of optimal is worth enough money, then solving the problem on a quantum computer starts to make financial sense if it's going to give you this small edge. So those are the sort of optimization problems that we're looking at sort of as the first use cases for quantum, are ones that you're solving approximately and where a slightly better quality solution looks like it has some value. I'll mention one just example that I learned about the other day, not decentralized energy, but energy at least, where we were talking about feasibility of just scheduling for generators. You want to turn them off and on. There's some uptime, some downtime. You want to repair them over the downtime, and you want to figure out a schedule for turning these things on and off again to keep meet power demands. And just figuring out a feasible schedule was, I was told, a hard optimization problem as your network gets big enough. So this is the sort of thing where there's a hard optimization problem out there that, if your classical system is struggling, now maybe you push it onto quantum and see if it can give you an edge. That's the flavor.
So you've been learning a lot about quantum today, but let me do some unlearning. So Adam and I think, have done a great job at putting quantum kind of as a special thing, right? But there's a risk to this. You might think that it will live kind of standalone in its own corner of the world, and that you really need to think, okay, am I using a classical computer or am I using a quantum computer to solve a problem? But ultimately, when we get to industrial scale applications, you will be doing supercomputing the same way you're doing supercomputing today. But in that supercomputer, there might be a QPU, the same way that there's a CPU and a GPU, right? And so if you look at your industrial business problem workflow, you can probably split that into 100 boxes of different steps of the problem, right? And some of them might be very easy, so do that on the classical computer. But out of the 100 boxes, there might be one or two that are actually really computationally hard, and that they might benefit from using a quantum computer. So even though your problem is going to be, say, 98% classical or solved by classical resources, there might be this tiny part that you offload to a quantum computer. And it might just be like, oh, I need to sample from a probability distribution that's no different than whatever classical computer can produce. And we know quantum computers, just because they behave differently, you can access probability distribution that are unsimulatable classically. But we don't know exactly this. But yeah, just wanted to make sure you understand. We're not talking quantum versus classical. It's classical versus quantum and classical. Does that make sense? Good.
I can add a quick comment on the distributed aspect. I think part of what you're getting at is that as we get to a more and more complex system, it isn't going to be centralized control. Each of these devices or subgroups of devices are going to have to make their own decisions about what to do to keep the grid stable and balance things out. But we're going to need to be able to forecast probably how that's going to look at the system level so we can keep everything balanced. So for example, as we just deploy our storage systems, they will be making autonomous decisions about whether to charge and discharge based on what's happening at the terminals, the voltage at that area of the grid. At a centralized level, there'll have to be some statistical or probabilistic determination of what's likely to happen and how much excess capacity may be available for other services from those distributed devices. And it's and then the planning side of it is the other part I learned, where I think it really will have a lot of impact, is deciding where to put these assets on the grid. And then, life, once they're there, life goes on and they run as they run. But if you make the best decision about where to put them, you're going to get the best usage out of the infrastructure that we've got.
We're down to 1 minute. So, oh yeah, go for it. If you got a quick question, let's do it.
Yeah, my question is, who's the champion? Because when you talk about, the complexity and now distributed energy resources, I know that in Saskatchewan we have a monopoly utility that is really looking to simplify the playbook. They're actually recapitalizing coal as kind of, it's jobs, and it's so. I see that the arguments default to sort of jobs or, sticking to the simpler things because that's what we know how to do. I see a tool here that can maybe help decision makers, but I don't know who the champion would be. Like, I'd like to hear about, who you think is really the advocate that can help, a jurisdiction like Saskatchewan here understand what the solutions could be.
I think the champion is load growth. So as the load grows, we said over the last 20 years there hasn't been a lot of load growth, so it's been easy for utilities to just kind of maintain what they have and keep doing what they're doing. But as you start to see load growth and you're looking at, okay, well, it doesn't really matter if we're talking about coal or hydro or solar or whatever it is, I just can't get that power down those power lines to where it's needed. There's no good solutions for that. The cost of upgrading the power grid right now, the materials that are required is 2 or 3 times what it was 10 years ago. Trying to get new rights of way to put in a new transmission or distribution line is not practical on any kind of time frame. So we've got to find new ways to use the infrastructure we have, and it's load growth. The return of load growth is really what's creating the pressure to do all of this.
Andrew, do you want to close that out? Looks like
Sure.
yeah.
Well, yeah, I'm just cognizant of the time here, but I think, to echo what Brent's saying, there's eventually we're going to hit limits, right, within the demand side of things, where we're going to be forced to have to optimize. We're going to be forced to have to reduce consumption, because if we don't make those changes, you're going to lose power. There's going to be brownouts. There's going to be these complex problems. So I wouldn't say there's one champion that's going to be out there, but the utility is going to be asking their high consumption customers to start curtailing more and start to share the load amongst others on the same distribution network, and so I think there's going to be a natural sort of inflection point where it has to happen, and we can't. So we need to get in front of it to help utilities and the consumers understand the impacts of the growth that we're having, and how we're going to have to make decisions in order to continue.
Great, gentlemen, thank you so much. I think one of the big takeaways is really just start the conversation. Come talk to us. Let us help you really along that journey. So thank you, gentlemen, and enjoy the rest of your day.